So, welcome again to the new lecture of the course, Properties of Materials. So, let us just briefly recap what we did in the last lecture. So, in the last class we looked at basically the band theory, and the origin of band gap. So, essentially band gap is basically what happens is that when electrons are travel in the lattice. So, when electrons are in the lattice, electrons undergo diffraction at certain reciprocal lattice points. So, let us say those are k plus minus pi by d plus minus 2 pi by d and so on and so forth. So, for this you will have to read a bit about the reciprocal lattice, but basically reciprocal lattice space is the same reciprocal space as we have wave vector. So, basically k is the reciprocal, you can say the wave vector which is in reciprocal space, which is 2 pi by lambda, and then capital K is the reciprocal lattice vector, which is of the order of some 2 pi by some distance d. So, it could be plus or minus depending on the direction, or let us say n pi by d. So, you can see both of them are reciprocal of length. As a result, they are called as reciprocal vectors. So, this is wave vector small k and capital K is the reciprocal lattice vector. We do not have time to get into this, the details of reciprocal lattice vector. Basically, when you have this energy band diagram E k, so instead of having continuous energy states, at certain point you have this diffraction by the lattice, and these points are plus pi by d, 2 pi by d, 3 pi by d, minus pi by d, minus 2 pi by d and minus 3 pi by d. It is at these points the band structure changes. So, the band structure now is essentially like this. So, these states are basically, you can say, the forbidden gaps. Okay. So, these are the gap states. Same thing will happen here also, you will have, so these will be the gap states. Now, we also saw, so these are forbidden gaps in which there is no energy state available. So, electron either exists below this or above this, but nothing is there present in the gap state. Now, what might happen in real crystals is that, let us say in real crystals, as we saw last time, that let us say along certain direction we have a gap state which is shown by this diagram, let us say. So, in one direction the gap state is like this. So, this is let us say at pi by d. So, this is let us say along 100 direction, okay. This is E and this is K. Now, if you take the same thing along different direction, so this is again K vector and this is along 110 direction. So, we can see that along 110 direction, if situation is something like, but 110 k vector will be different. So, let us say the k vector now is square root of 2 pi by d, and at this point the curve follows like this. Okay. So, we can see that although when the electron is travelling along 100 direction, at this k value it encounters a gap, but it can change its direction and find the energy state in different direction up to this point. So, effectively the gap is essentially this, because corresponding to this region there are states available here, corresponding to this region there are states available here. So, electron can always transition from one direction to another direction and find energy state, but in between there is a region where there is no state available. So, this is no state available. So, this is basically the forbidden gap. So, let us say, so this is basically across the, and if this continues across the K space along all the primary reciprocal lattice directions, then you will have a forbidden gap. Suppose the situation was something like this. Let us say I redraw this diagram in different way. This is K, this is K. So, this is again let us say 100 hypothetical situation, this is again 110. Let us say the situation was that we had a situation like this, and then for this direction at square root pi by d, this is pi by d. If the situation at this point was that the energy gap went like this, use a black color. Then we can see that for this region, for this gap region, I have states available in this region, and for this gap region I have states available in this region. So, I can see you have states available here, in 110, and here you can see the states available in 100. So, basically this material does not have a it has overlapping bands. As a result, electron can transition. So, when it reaches here at this point, it sees a gap along this direction, but it can transition itself to 110 direction, and when it reaches at this point, it can transition itself to 100 direction. So, there is not a continuous gap that exists in these materials. So, if you have a situation like this, then what we make is a metal, and if you have a situation like this with a forbidden gap, then what we make a insulator or semiconductor. So, we also saw that for monovalent and divalent, for monovalent and trivalent metals, for which the electronic configuration is not complete, they have partially filled bands. As a result, for these kind of materials, if you take, this is valence band, this is conduction band. So, this is conduction band, this is valence band, but valence band is partially filled. So, it is up to, let us say you can have a gap here also, let us say, but there is an overlap of states. So, and to avoid the confusion, just let us not just draw the conduction band. So, it is the valence band, and this will be the, basically you can say the Fermi level at this point. So, this will be the Fermi level. So, this is, you can say, a partially filled valence band. Okay. In this, in the case of divalent metals, where you have outer shell filled, what will happen is that valence band is filled. So, this is valence band which is filled, but then the conduction band is partially overlapping. So, this is conduction band. So, electron can always transition from here to here. So, this is basically overlapping CB and conduction band and valence band. So, this is what happens in a divalent metal. In group 4 elements such as carbon, silicon, etc., what happens is that there is a gap. So, this valence band, so this conduction band is separated with respect to valence band. Valence band is completely filled. So, this is completely, so we are taking at 0K, okay, at 0K, and this is completely empty, and these two are separated by energy gap Eg, which is called as energy gap. So, in case of diamond, it's this magnitude is very large. So, in case of diamond, it is nearly which is carbon, which is 5.4 eV, but in case of silicon this is 1.1 eV. If you come down, germanium it's 0.7 eV, and in case of tin it's 0.08 eV, and in case of lead this gap is down to 0. So lead and tin are metals because the gap is very small, but diamond, silicon, germanium are you can say semiconductors slash insulators. So the way we define semiconductor and insulators are, semiconductors are materials with band gap of 2 to 3 eV, Eg. Okay. Insulators on the other hand greater than 3 eV is the Eg for insulators. I mean, this is a fuzzy boundary 3 eV, some people say 2.5 eV, 2.6 eV, and in case of semiconductors anything when Eg is more than 2 eV we call them wide band gap semiconductors. Now let us go back to one more thing that we talked earlier. We said earlier that when you have conduction, so in the Ek space, if the minima of conduction band and maxima of valence band they coincide each other, so when K minimum in conduction band is equal to K maximum for valence band, then this is a direct band gap material, and in the context of semiconductor we call it direct band gap semiconductor. And if this conduction band minima and valence band minima they do not meet with each other, if there is a difference between the K, so K minimum conduction band is not equal to K maximum of valence band, then it is called as indirect band gap semiconductor. So examples of this are, for example, silicon, germanium, both are indirect band gap semiconductor, and if you take example of gallium arsenide, this is a direct band gap semiconductor. There is a fundamental difference here, because if electron has to transition from here to here, then it has to change its, so it cannot do so easily because there is a change in K value as well, because if it wants to go from here to here, then there is a change in K value. So there is a change in K value, and K is basically, you know, we saw that K is nothing but related to momentum. So there is a change in momentum in this case, whereas in this case the electron directly is able to transfer from here to here. So there is no change in K. So as a result, indirect band gap semiconductors have lower optical absorption efficiency or lower absorption coefficient, and direct band gap semiconductor have higher optical absorption. There are other differences as well which we are not going to get into details of, but this is a major difference between the two materials. Direct band gap semiconductors are those where K min and K max of conduction and valence band coincide. As a result, when electron has to transition, suppose you have a light coming at certain energy, if the h nu is more than Eg, then electron directly goes from here to here, creates an electron hole pair. So there is no change in the K value. So as a result, the materials of such nature absorb light easily. In the case of this kind of situation, the electron has to transfer from maxima of valence band to minima of conduction band. As a result, there is a change in K value, or if it has to go from here to here, then it has to use higher energy. So basically, when h nu is greater than Eg, absorption will occur, but either there will be a change in K value or you will waste more energy. As a result, the optical absorption efficiency is lower, or optical absorption, light absorption is lower for the same band gap. Okay. So, this is a fundamental difference between the two materials. So, this is a brief background on what are semiconductors, what are insulators, and what is the origin of bands and materials and stuff like that. We of course haven't been able to go into too much of details, but this is the bare minimum we can do for such an introductory course. Now, let us concentrate mainly on semiconductors. And why we want to do that? Because semiconductors are very important materials. They are used in a lot of electronic applications. They are the backbone of electronic industry, microprocessor industry, and as a result we got to know about the properties of semiconductors. So, essentially semiconductors are the materials which have a band gap, we can say less than 3 electron volt, and so this is basically we say it is a forbidden energy gap. Okay. So, essentially if you plot this energy band diagram of a semiconductor, so this will be valence band and this will be conduction band. If you have electrons here, so at 0 K this will all be full, so here energy is going up and this is distance x. Okay. So, this is full at 0 K, this is empty at 0 K. The moment you increase the temperature, this electron has certain probability of crossing this energy gap. It goes to this conduction band and it leaves a hole here. Okay. So, this is basically when E is greater than Eg, your electron from valence band has, or we can say that at T greater than 0 K, electron in valence band has finite probability to cross over to conduction band, and this probability is basically 1 over exponential of minus of Eg divided by 2 kT. So, at a finite temperature, depending upon the band, so this is proportional to N, so N is proportional to Pe. So, essentially at a finite temperature for a finite band gap, electron has finite probability of being found in the conduction band. As a result, even at very low temperatures, you will have certain number of electrons in the conduction band which can be excited from valence to conduction band. So, essentially there is a relation between the carrier concentration. So, let us say semiconductor is pure, it does not have impurities. In this case we call it intrinsic semiconductor, and in most cases we take example of silicon. And for silicon we will see this as we for a given temperature there is a finite probability, and this is related to conductivity. So, this is conductivity is proportional to N, which is proportional to probability of finding electron, and basically you can see that from this you can see as the temperature increases, N increases and then sigma also goes up, and this is basically opposite to what we see in metals. This is one major difference between metals and semiconductors. So, in metals, as temperature goes up, conductivity goes down. In semiconductors, as temperature increases, conductivity increases because N increases. Okay. So, essentially now approximately we can also approximate this situation, let's take example of silicon. Okay, silicon has a band gap of about 1.1 eV. So this is the Eg of silicon, and so basically this is approximately the energy difference between an ion which is close to an electron which is or a place which is close to ion core, and then a place which is away from the ionic core. So let us say the distance between two such locations. So these are silicon atoms. Let us say silicon has a diamond cubic structure, by the way. So if you make a crystal structure of silicon, so silicon will have, so you have silicon atoms here, 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 and then 4 atoms of silicon in the 2 here and 2 there. So these are all tetrahedrally coordinated silicon atoms. So diamond cubic structure. So distance between one location to another location, let us say, is approximately 1 angstrom. Okay. So this is the energy that is required to move the electron from one location to another location, which is about 1 angstrom, let us say. So if you apply, so if you essentially what you are saying is that, and if you approximate this as 1 eV, what you are saying is that you require a field gradient of, so if you calculate the field gradient, it is 1 volt divided by 10 to the power minus 10 meter, or 10 to the power 10 volt per meter to move an electron from the top of valence band to conduction band. So if you look at the valence and conduction band picture, you are going to move an electron from, so this is conduction band, this is valence band, you are going to move an electron from here to here. This will create electron here, and empty state here, which is called as hole in the language of semiconductors, and this will take an energy of basically 10 to the power 10 volt per meter. So it's a lot of field which is required to move. And now this field is not possible. So even if you let's say have a crystal of, let's say, crystal of size 1 micron, even for 1 micron size you will require a field of 10,000 volt, which is like 10 kV of field, which is a very large amount of field. So basically applying a voltage is not the way to excite electrons. So the only way by which you can excite the electrons, so voltage application, large voltage application is not practical. To excite the electrons. So what do you do? So as we discussed earlier, the other way is thermal excitation. So thermal excitation is essentially at room temperature, the thermal energy that is available. So at room temperature, which is about 300 Kelvin, the thermal energy can excite sufficient number of charge carriers, that is electrons from Vb to Cb, and when you excite electron from Vb to Cv, you create electron here, and what you create, this is called as a hole, which is basically a empty state. So of course when the gap is very large, like diamond or some other material, it's not possible to do, or alumina, but if it's like silicon or germanium, it's easier to do. So this is, so thermal excitation is possible and feasible in low band gap materials, such as example silicon, germanium, and so on and so forth. So in intrinsic semiconductors, so this is basically, so thermal excitation is the major process which happens, which is applicable for mainly for electron density, electron/hole density in intrinsic semiconductors without any impurities being present. So, so number of electrons that can be excited, so we can say the number of electrons that can be excited from top of VB to bottom of CB, they can be given as so for this we use what we say Fermi-Dirac statistics. So we can say the PE, the probability of finding electron, is 1 over 1 plus exponential of E minus EF divided by KT. Now for a semiconductor like this, the position of EF is always in between. So this is, let us say, conduction band, though the bottom of conduction band is always defined as energy EC, which is conduction band edge, and this is valence band, and the top of valence band is defined by energy EV, which is valence band edge, if you take this as E, and the distance between EC and EB in terms of energy is EG, which is the energy gap. So basically EG is nothing but EC minus EV, okay, and the Fermi level for a semiconductor lies midway, which is at EG by 2 location, okay. So Fermi energy lies always in the midway. So, and we say that probability of finding electron at EF is 50%, even though, let us say that even though there are no energy states in this gap. So basically we are saying that E minus EF is equal to EG by 2, where EG is basically the so the denominator here, E minus EF, that we can write as E minus EF as EG by 2, and if you take for silicon has EG of 1.1 EV, so EG by 2 will be 0.55 EV, and if you take whereas KT at RT is nearly 28 MeV, if you can calculate. So just put the value of Boltzmann constant and temperature and room temperatures, so basically 1.38 to 10 to the minus 23 joule per Kelvin into 300 K divided by 1.6 into 10 to the minus 19 joule per EV. So this will turn out to 28 MeV, which is very large, about 20 to smaller. So as a result, one can say that the factor, so you can say that PE was equal to 1 over 1 plus exponential of E minus, so this is EG by 2 KT, okay. So we can say that this factor 1 is basically ignored because this is very large. So as a result, we can write this probability PE as exponential of minus of EG divided by 2 KT, and so this is a very simplistic analysis. So as a result, the number of electrons that can be excited across the gap is equal to some constant n into exponential of minus of EG by 2 KT. N has a value which is basically NC into NV divided to the power half, and NC and NV have certain expression. So we can write the value of let us say NC and NV. So this can be written as, so this product of NC and NV can be written as 2 Me star KT divided by 2 pi H cross square to the power 3 by 2. This is what basically it is, and so essentially this is this you can say is the electron concentration. So, electron concentration is n some constant, which is basically effective number of you can say the number of electrons available for excitation from top of valence band to conduction band. So, or you can say effective density of states Nc and V. So, Nc is the effective density of states in and Nv is effective density of states in Vb. So, we have not done the whole derivation, but this is basically what it is. So, and product of Nc and V is given as 2 into Me star kT divided by 2 pi H cross square to the power 3 by 2, where H cross is H divided by 2 pi. So, this is what we have done. This is the carrier concentration in an intrinsic semiconductor as a function of band gap and temperature. And we can see as the temperature increases, the number of electron increase in the conduction band in an intrinsic semiconductor. We will do this analysis little bit, effect of impurities and conductivity of such semiconductors in little bit more detail in the next lecture. Thank you.